Welcome everyone, this is Mustafa Atalla, a PhD researcher at TU Delft in the Tactile Machines Lab and Byte Group, and today I'm presenting our research about near-field acoustic levitation liquid environments as part of the poster presentation in the International Ultrasonic Symposium 2022. When two objects are placed in close proximity to each other and one of those objects vibrates at ultrasonic frequency, it was found that a pressurized film fluid is created which levitates the two objects away from each other. This phenomena is called near-field acoustic levitation or squeeze film levitation, which has been exploited in different applications including friction modulation of haptic displays and squeeze film bearings. In all of these applications, however, levitation occurs when the surrounding fluid is only air. Having the same ability to levitate objects in liquids could bring this phenomena to a range of applications where liquids are omnipresent, including medical applications. Earlier studies have shown that it's indeed possible to attain levitation in liquid environments. However, none of these studies provided an explanation of the physical underpinnings of this phenomenon, which indicates a gap in understanding the physical principles behind it. By revisiting the existing theories, we find two leading theories in modeling near-field acoustic levitation. The first one is the lubrication theory, whose formulation predicts no steady-state levitation in incompressible liquid environment. The second leading theory is acoustic radiation pressure theory, which was proved not to be suitable for fluids confined in thin films. In this research, we show that fluid inertia is the main contributing factor to the near-field acoustic levitation phenomena in liquids, demonstrated by an analytical model validated experimentally. Using the pressure profile formula developed by Kuzma et al. For liquid squeeze films with inertial effects, and assuming a free-floating mass in close proximity to a vibrating surface with liquid film in between, we can find the following equation of motion for the free-floating mass using basic dynamics analysis. By simulating this equation of motion using a sinusoidal vibration input at ultrasonic frequency and micron level amplitude, we can find the response of the free-floating mass, which does predict a steady-state levitation agreeing with the experimental results from the literature. We also conducted an FEM simulation based on a fluid structure interaction framework, which agreed with the analytical model we described earlier. By looking closely at the response of the free-floating mass, we can find two characteristic time scales. The first one is the ultrasonic time scale, and the second one is the levitation time scale. Using this observation and by conducting a time averaged analysis, we obtain the following expression for the steady-state levitation height. This expression predicts the steady-state levitation height to be proportional to the area of the disks and the angular frequency and the vibration amplitude and the density of the liquid, as well as the phase shift, and to be inversely proportional to the mass of the free-floating object. To confirm the theory, we have built the following experimental setup, which directly measures the levitation height of a free-floating mass facing an ultrasonic vibrator while tracking the vibration input. First, we confirmed that it's indeed possible to obtain steady-state levitation in liquid at different vibration amplitudes. And by comparing our model predictions to the experimental data for 3 different masses, we find that our model aligns well with experimental data validating the theory we are putting forward. By conducting the same experiments in air and liquid, we find that levitation in liquid is significantly higher than its air counterpart. To conclude, we showed that the fluid inertia is the main reason behind in-liquid near-field acoustic levitation. We developed a model incorporating the liquid inertia as well as the levitated object dynamics. We derived the formula that predicts the steady-state levitation height. We validated our model experimentally, and we demonstrated that in-liquid near-field acoustic levitation is significantly higher than its air counterpart. Thank you for your attention, and feel free to reach out with any question about our research. Thank you.